Hello.
Hmm?
So welcome to our first colloquium
Oh,
after
what happened?
first in-person colloquium after 2 years. So this is a great event for us. And look who is here, a friend of the house, Mike Shub. So I don't know if you all know him. I know Mike since July 1995 in Park City. So that speaks about my age. But so, and we became such good friends so forever, and Mike started to be my mentor somehow. So my mentor in my academic life, and I have to thank him for all what he did for me. But now today we are here to speak about him, not me. So Mike got his PhD with Steve Smale, and it was on dynamics. And if I remember well, at some point you told me that at that time dynamics was such a new field that it was difficult for mathematicians to absorb it, because it was not algebra, geometry, topology, or whatever. It was not a compartment. It was all together. So you told me at some point you sent a paper to a journal, and they just rejected it because they didn't have any reviewer, because it was too difficult at the time. So imagine now dynamics, no? Everybody speaks about dynamics. And then after many years, with Steve, they switched it to real complexity. So they changed from dynamics to real complexity. And Mike is together with Steve and Lenore, the responsible for this BSS computation model that you might have heard about. It's kind of the real counterpart of the Turing machine. And this is the model we use for real complexity. And so Mike, he also has this series of very famous papers with Steve, the Bezout series, like 6 or 7 papers, absolutely fantastic on real complexity. And then Mike is coming back to dynamics, no? Yeah, his heart is coming back to dynamics. And he's a distinguished professor at CUNY. And welcome, Mike. I'm so glad to have you here.
Thank you very much, Teresa. Does anyone object if I take off the mask? Okay, thank you. And, but now I've just undone my ear. Let me see if I can put it back on without. Is that good enough? Yeah, okay. So I know my English is very hard to understand, and my handwriting is terrible. So so I've tried to write almost everything I'm going to say down on paper, and I'll try to simultaneously leave it up as I write on the board, probably more or less the same material. So let me just start out with a little historical story. Steve Smale was my advisor in dynamical systems. I think he got involved because he met Mauricio Peixoto, and he was in the middle of doing his, and René Thom, and he was in the middle of turning the sphere inside out, proving the Polynomial conjecture, all that, when he also started on dynamical systems and had some very naive and very optimistic ideas about how the subject might go, I might say. But I think it was like very rapid, that his involvement, and then by around 1969 he started to study mechanics, moment maps, things like that, relative equilibria, and then shortly after moved on to economics and relative equilibrium in economics. And I think it was around 1976, there was a conference in the Marseille Meeting Center, Lumini, which wasn't yet built, the housing wasn't built, and everybody was staying in small towns nearby. And there was, it was a conference on mathematics and economics. And somehow I was invited as a young participant. And there were these guys from Princeton and Yale and Steve, and they all had algorithms for finding relative equilibria. So the guys from Princeton and Yale were more or less doing simplicial approximations. Steve had a kind of Newton's method, and everybody's talking about the same problem with many, many different methods to solve it. And so Steve started to think, well, how do we compare these? I mean, we want to judge which is the better method, and we don't have in sort of that type of mathematics a model that's like the Turing machine model for studying complexity and theoretical computer science. So he then picked a specific problem that he was going to study and that could somehow expose the principles of how such an analysis should go. And the problem he picked was to find the roots of a polynomial equation. So he starts his work around 1980, I think. The very first work, it was actually, if you think of the polynomial mapping from the complex numbers to the complex numbers, he says, take a point, and you look at a p of z naught. So you know the solution of the equation p minus p of z naught. You've got one, it's z naught. So now you just take this point p naught, z naught, p of z naught, and you draw a straight line to 0, and you start solving p minus t times p of z naught, where t goes from and if this curve doesn't hit the critical values, you can always lift it back to a curve here from z0 and follow the inverse of the curve back until you get a root. So that was the sort of the method, the analytic continuation, but the actual method was to pick the t's. So if you have t1, t2, tk, tk plus 1, how do you get tk plus 1 from tk? Well, you look at the equation p of z minus tk plus 1 times p of z naught, and you use Newton's method So if you know the solution for tk, you're close enough to it, then you use Newton's method to approximate the solution for tk plus 1. And then you keep moving in this until you get some stopping criteria which he defined. And he then also studied the space of polynomial systems, which he took to be a polydisk, and it was just p of z for degree d is e to the d plus ad minus 1, z to the d minus 1, plus a0. And then we took, say, the absolute value of ai less than or equal to some constant. In fact, he took the radius to be 1. And then he proved his theorem. He gave a colloquium talk. I was there at Berkeley at his talk, and he says that this method, if you look at the volume element here on this polytope, and you ask how many steps it takes to get to the stopping criteria. He said, okay, you get to the stopping criteria, and the average amount of work you do, well, I think he proved the number of steps you needed to do of Newton's method was something like at most 1 over sigma to the 7th, where sigma was the probability of failure, that you didn't actually meet the stopping criteria. So he was happy he had sort of a polynomial estimate in the amount of work you needed to do in terms of the arithmetic complexity of the computation, and he had a polynomial answer in the probability of failure. So sort of had an overall polynomial. So then that's the point at which I started to get involved with him, because I said, Steve, this is an infinite average cost algorithm. 1 over sigma to the 7th integral is infinite. So it means you've got an algorithm that's going to be infinite average cost. So even though it's sort of polynomial in the probability of failure, it's got a drawback. So then we got involved together in studying other algorithms like, sorry. See if I can do this properly. Studying other algorithms by maybe choosing the point z0 a little better, and then proving that if you chose z0, say, uniformly on the circle of radius 3, or even if you took a nice discrete subset of the circle of radius 3, you got a polynomial answer. So we could go to the so at first it was infinite, and then Renegar actually studied systems of n equations and n unknowns, but now I think his number of steps, probability of failure was something like 1 over sigma to the 23rd, if I remember. So somehow sort of worse. Still polynomial in the probability of failure, but infinite average cost. So then what did we do? So this was all, oops. Oh well. Is there a better method? Maybe there's maybe I'll use a different pen. Oh, no?
Okay, I can help you.
So, yeah. She says, oh, thank you. Maybe that one's a little better. You won't let me use it? I have to use this one?
Yes.
Okay. All right. All right. So what did we do? Well, we did a bunch of changes. First thing, we changed from the space of polynomial systems from the polydisk. Oh, great. Thank you. From the polydisk to projective space, we homogenized the polynomials. So that now we're discussing h of d just to be homogeneous polynomials of degree d in n variables. Maybe n plus 1 variables. And so then we take h of d to be the product of h of di, I equals 1 to n. So n homogeneous polynomials and n plus 1 variables. They're supposed to have product di roots. That's Bazou's theorem. In the generic case, of course, you could have infinitely many roots, but almost all polynomial systems will have product di roots. I'm talking about over the complexes. So then what do? Well, the roots actually should lie in the projective space of Cn plus 1. So we have this variety V contained in P of Hd cross P of Cn plus 1. So if you multiply the system F if you multiply lambda F and F, they have the same zeros. So you might as well think about projective space. And if you multiply the point by lambda, it also, if it's 0, it also stays 0 by homogeneity. So the roots naturally lie in the projective space of Cn plus 1. The systems naturally lie in here. And this should be the variety of Fz, such that f of z equals 0. So for me, that was a very important and good change that we made for several reasons. One, the problem is compact. So now, the compact problem, you can bound things fairly easily. Second thing is, you can sort of check if your definitions really make sense, because you make a definition in affine space, but it has to make sense on projective space. So now it sort of corrals your definitions into ones that are sensible in projective space. That clarifies things a lot if you go ahead and check this at every stage. Oh, what I'm doing, does it make sense in projective space? Rennegar was working in affine space, so you constantly had to worry about the norm of the point that you're working at, because the estimates on derivatives and things like that all get involved in the norms. But in projective space, life is much easier. So then there's these two projections. This was another, for me, have these two projections of the variety V. And what we're interested in is giving a system. We want to study the points that make it 0. That's a finite fiber here. But this map is complicated. This fiber is, well, what you want to find out about. This fiber is a linear subspace. If I fix a point and I ask which systems vanish at it, that's a linear subspace. So that's not a complicated object. And if we want to study things like average number of roots that have a very bad inverse of derivative. So we could ask, okay, that's a statement about systems. Well, if we want to find the average, we'll have to integrate something here. But what we can do is we integrate here, and then we lift it to V, and then we push it down here. So we take a problem that's about a finite collection of points, and we turned it into an integral over linear subspace. And so we did that a lot for studying things like the norm of the inverse of the derivative. So what do we have to do? For one thing, well, we want to solve a system, so we start with some system and root we know. Like zi is z to the di times z0. So we take some system that we know all the zeros, and we call that f0, and then we connect it to a path to the one we want to solve, and then we go up to the solution variety, and we lift the path. So here we start with the solution we know, and we lift the path to find the solution of f1, and the way we do it is we mark off ft as before, and we start moving this point over by a Newton's method, but now we use something called projective Newton instead, because now the derivative goes from n plus 1 space to n space, so it's not invertible. So what you could just say the projective Newton method of f at the point z is z minus the derivative of f restricted to z perp applied to f of z. So now z perp is the natural tangent space to the sphere or to projective space. So what you've just done is you said, okay, I'm going to restrict to the tangent space of the manifold I'm talking about and use the Newton's method in that context. And now you do the same. You use this Newton's method. It's also the case that if you're at a zero, it's zero on the whole ray, right? So the derivative is zero in the direction of the ray. So if you want to invert it, you want to invert with respect to the complement of the ray. Again, the tangent space or projective space. So you, maybe I should go forward with the page here. It might be something readable. Whoop. Yeah. Okay, so that's it. Now we have a metric to put on PhD. We've got a natural metric on projective space. You just take the Hermitian metric in Cn and you divide by the norm of the point you're going through. That's now scale invariant, and so that defines the metric on projective space. What about the metric on HD? Well, you take a monomial, you make the monomials, maybe I won't make it norm. Oh, good. So I take the monomial x to the alpha, which equals x1 to the alpha 1 up to xn to the alpha n. So that's a monomial. All the monomials are orthogonal to one another, and x alpha with x alpha is 1 over d choose alpha. Ah, that's terrible. So that's the Hermitian structure we put on PhD, and you have to check that it makes sense. The main thing about this Hermitian structure is it is invariant under unitary substitutions. So if I have f of z is 0 and u is unitary, then f composed with u inverse u of z is 0. So the unitary group operates on v. un plus 1 operates on V, and it operates by isometries. And of course you can take by unitary transformation any point in projective space to another point in projective space. The unitary group is transitive on projective space, and also it is transitive on the tangent bundle. Okay, so that's the situation that we were in, and we were using this structure to study how hard it is to find solutions of polynomial systems, and we sort of got an algorithm that would show that you could solve systems in polynomial time to find one root on the average. Find one root on the average now with polynomial time. That's a lot better than 1 over sigma to the 23rd possibility of failure and number of steps. So one day I think I was visiting, I used to work at IBM in the research division. It was a great job. I remember interviewing it. I was talking to Shmuel Winograd, and he was the chair of the math department there, and they were recruiting me and were discussing what the job would be like. So I said, you know, I only go to university 3 days a week. The other days I may be going to seminars at other places, things like that. He said, okay. You only come to work 3 days a week. I said, well, you know, I only go to university altogether 8 months a year. Other times I go traveling to other places to get stimulation, work with colleagues. He said, okay, you take off some months a year and go traveling, and not only that, you have a 12-month salary, and we're going to give you money for travel expenses. It was a fantastic job, and it lasted until IBM in a fantastic way, until some point when IBM started to get under financial difficulties. So one summer, or no, not so, you see, that was the other great part of it, because I could take this 4-month period in the winter. And so when other people were free from their university jobs in the summer, invite them to IBM. They come to IBM in the summer. Nice to be in New York in the summer. And in the winter, I go visit them at their universities. So this was some winter time, and I was living Beata in a house in Albany, I remember. And one morning I get up and for some reason, I decide to do this computation to try to find out how many roots a real system has. So I'm sitting at my kitchen table in this little place we had rented, and doing the computation. It's taking a long time. It's a long computation. And suddenly the answer comes out, and the number of real roots is on average the square root of the Bezout number. I must say, one of the happier scientific moments of my life. It was like amazing. Real roots on average, square root of di. Product. D sub, oh, thank you. So the complex roots are the product of di. The real roots are the square root of the product of the di. which is great because the extension is degree 2, and 1 over 2 is the square root, so maybe there's some relation there. And in fact, I think you could probably prove such a theorem in other contexts, like the p-adics. But I don't think anybody ever has. Okay, well that's... Well, you have the same Hermitian structure, just restricted to the real systems. So that's now a projective space over the reals, polynomial systems, with this Hermitian structure on it. So now that induces a volume element on that projective space, and it's respect to that volume element that I'm taking average. Okay, so that's and in fact the algorithm that Smale and I made up, it was kind of you had to make random choices in the middle of the algorithm, so it wasn't precisely a deterministic algorithm. And Smale then asked the problem, one of his 17 or 18 problems for this century, about whether or not one can do a deterministic algorithm that would find one root of a polynomial, complex polynomial system in average polynomial time. And a lot of people worked on that. Steve and I wrote a sequence of papers, Beltran and Pardo, Berger, Kuker, and finally this young French mathematician, Pierre Lérez, solved the problem. It was actually a fantastic piece of work. Recently, Philippe Kuker wrote a survey about all this progress, and you can probably find it on his website or something. Okay, so that's that story. So that's just repeating what I said about the Hermitian structure. What you have to do. Unitary group. And this formula about finding the number of real roots. So you want to integrate this function here. This is now the real projective space. The function you want to integrate is the number of points in the fiber, the number of real roots. So but instead you can lift it here and multiply it by the Jacobian of the projection. That will give you the same integrals, just change of variables formula. But then when you got it up here, you can disintegrate it over here, and you do that, and then you just follow the computational along. And what happens is everything cancels out. It turns out that the computation only depends on the derivative of the polynomial system at the root, so it doesn't depend on the higher order terms. So you project on the sort of linear systems, but you have to use that this Hermitian structure on the linear systems, and the change of variables gives you precisely this number. Everything else goes away. Because the solutions of average number of solutions of linear systems, you happen to know that's 1. Right? So this just pops out, and somehow it's just because of the change of Hermitian structure that is caused by looking at the unitary invariance. So the unitary invariance, if the problem's unitary invariant, it'll give you the same answer for every fiber here. So you only have to look at one fiber, one linear space, and then you get rid of all the other higher order terms, and then you get the linears and blah, blah, blah. And this pops out somehow. So if you actually, in the book that we wrote with Philippe Kuker and Lenore and Steve, the proof is there in one of the chapters of the book of this theorem. But actually, for many years, I don't really understand this proof. I keep wondering, what is this proof about? How come you get the square root of di, and it comes out and it seems to have nothing to do with the problem almost? I mean, it has to do with projective space and the Hermitian structure on the linear maps, and it has to do somehow with reducing to the linear maps. And but yet, for decades I've been wondering. I still wonder a little about what it means. And so, so here I sketched out how the proof comes. You wanted to do that Jacobian on the previous page, so now you lift it up to V, but on V you disintegrate it over the other fiber, and so now you figure out what the ratio of these two Jacobians is, and it's just the determinant of the adjoint to the derivative of the derivative, and then because it's all invariant under the unitary group, you can assume that your root is E naught, so all the things are zero except for Z naught, and then you disintegrate the higher order terms onto the linear maps, and you know the answer for the linear map. That's how the proof goes. I think actually that's a better version of it than is in our book, I think, if you have to retranslate. Because I think in the book it's just like when I was at my kitchen table and just computing. So it's like, you know, one step goes another step, all of a sudden you end up with the square root of di. A friend of ours actually came by that afternoon, just after I finished the computation. And so he rings the bell and he comes in, I opened a bottle of champagne. It was, okay, so well, I should mention that Eric Koslin proved a version of the theorem where all the d's are equal, which was a different proof. So here's now a theorem. Projective space, homogeneous space. This is the... So where does the theorem lie? And so now I'm going to say that in some sense, up to finite distortion, every manifold is a homogeneous space. As strange as that may seem, homogeneous spaces are very special, but it turns out, and I believe this is correct, so I taught a course last fall at the CUNY Graduate School, and one of my students is supposed to be writing the proof of the theorem that I claimed in the class. So this map take a closed manifold, let's say, compact without boundary. Then you have this map, natural map, from the diffeomorphisms of M, across M to M, which is, I'll call EV for evaluation, and it takes Fm to F of M. So that's like the unitary group operating on projective space, and you just take the orbit of every point, and this map is first of all a locally trivial vibration. It's a submersion onto the manifold. You fix M, it maps M to any other point in the manifold, it maps onto all the jet bundles that you'd like. It's transitive on the tangent bundle, it's transitive on the Grassmannian of K-planes in the manifold. it's everything. So it's like it's even, you know, better than the unitary group. But this is an infinite dimensional manifold. So the question is, first question is there a finite dimensional approximation to this with the same properties? So I'd like to find a compact manifold, H, and either a submanifold of diff or an embedding in diff with the same properties. What properties? Well, this evaluation map for any point M is again a surjective submersion. Maybe for any 2 points, if I look at a delta, so now it's a compact manifold, right? So the fiber is compact. So I look at a delta ball in the fiber, and I want to, for a fixed delta, to represent a fixed proportion of the volume of the fiber. So that's, if the manifold is compact without boundary, then that's automatic just by continuity. Then I want it to act transitively on the cross-binding of K-planes in the tangent bundle. So I tried actually to prove that there is a compact manifold without boundary with these properties, and I failed. I don't know how to do it. It must be true. I mean, you just sort of make it bigger and bigger. Sort of locally you can do it, and then you're going to piece them together, sort of make it manifold bigger. You've got a lot of dimensions here. It's infinite dimensions. So you just start with some compact submanifold that'll be submersive on some part. Take another manifold that includes it, still compact, increase the dimensions, and get a compact manifold with these properties. Well, I think it should be true, and it's a nice open problem. I didn't see how to do it in the end. But a compact manifold with boundary is not such a difficult problem. You can just take submanifolds of the space of vector fields. So for example, on the torus, you could just take the parallel vector fields from the torus, and that'll be transitive, certainly on the torus, and then you can add in some other stuff to make it transitive on the tangent bundles. And for torus it's easy. For other manifolds you can do it locally. In fact, it's in Durham's book he discusses doing this locally. So the book is from the 50s on the but what's it good for? Well, now I want to prove this theorem on square root of di or something like it in this context. And so here it is. If you got one of these, and I say you do, because you have one with boundary, then given any 2 submanifolds of complementary dimension, any 2, I want to know how many points of intersection there are on average when I move one of the manifolds around by this collection of diffeomorphisms. So I've got freedom to move one by any one of these, and I keep the other one fixed. How many points of intersection do I have? And the theorem is it's comparable to the product of the volumes. Oops. There are constants above and below. For the below, this ratio of the volumes comes into play. So you have to be a little bit careful, because like if you take the circle and you just map around 1.5 times with an open interval, that's a submersion onto. But you may get into trouble where the number of points changes from 1 to 2. and the number of points in the fiber. But I say you can do that with manifolds with boundary even. And then you get the ratio of the number of points of intersection being proportional above and below to the volumes of the two. So how does the proof of that theorem go? Let me just okay. When you have this picture, so V is now going to be H in this thing, H, V and W, such that H of V equals W. So V and W are submanifolds of M. And when you have this situation, now I'm going here to H, and here comes the projection to V cross W. When you have this picture, the number of points is given by the sort of local solution map. So if I give you an H here, and I give you a V, such that H of V is HV is in V, then there's a kind of local solution map, G of H, such that G of H lies in V. And then this integral of the number of points is given in terms of the integral of this solution map in terms of the determinant of, I don't know, G star, derivative of G star G. This determinant of the derivative of G star, something like this. Actually, I may get some of these things wrong, but they're in the book, with Kuker and Blum and Smale. There's formulas in the book. In the same chapter is computing the square root of di as the number of real roots. So you have to do this, but now what's G? Well, it's given by implicit differentiation. So what did I do? Oh, here it is. So you implicitly differentiate, and then you write down what the derivatives amount to for this G, and then you pull out two parts. One is the evaluation, so the derivative of evaluation is linear, so it just evaluates tangent vector at V, and the other one is depends on the amount of transversality you have, but then you have to integrate this, and because it's compact, the derivatives of this one are bounded, and you have to, on some big enough set, this one, I think because of the -1 here, this inverse is no problem, that's a bounded map. This inverse could be trouble, but it's a submersion everywhere, so if you have linear maps and you look at this onto linear maps and you take their adjoint with the map, that's again, if the thing is compact, bounded from above and below in its norm. So you get both of these, and this one you have to bound from below sometime, but that's that other condition about occupying a volume. So that's how the proof of this theorem goes. And maybe I'll stop there. Thank you.
Are you sure you want to stop?
Hmm?
Are you sure you want to stop? You wanted to say something about the dynamics or the
Oh.
origin of the problem. Or
All right, so let me take a sip of water, then I can tell you my fantasies. I want to prove what's called the C1 entropy conjecture. So this entropy conjecture I made in 1972, and it was proven for C infinity maps in 1985 by Joseph Yamden, but it is open for CR maps for all finite R. So I think it would be wonderful to know this conjecture for any finite R. But I was, sort of vaguely thinking maybe even C1. So I want to prove it for C1 diffeomorphism. How much time do I have for this? 5 minutes. Okay, so in this, my idea is somehow I have two manifolds of complementary dimension. I have a diffeomorphism F, and I want to study the intersections of F to the n of V intersect W, and I'm going to let n go to infinity, and I want to know how many of them are delta apart for some finite delta. That's the growth rate of that number. That is the entropy, and I want to compare it to the homology of the manifold M. So I want to say that the predicted number of points of intersection is given to you by evaluate the homology class represented by V on the cohomology class of W, that given to you by intersection. So that should give you a lot of points if you've got a large eigenvalue in the homology. So suppose V and W represent somehow these homology class and its dual, and I'm going to look at the algebraic number predicted, and I want to say that these points can't all be staying together closely all the time. In order for really to get two different points of intersection with the same index, the points ought to move apart. If they stay close, it's going to look like that with one positive index and one negative. They're going to cancel out. So I'm going to say the homology information has to give you a lot of points that get apart at some moment. If they stay too close together, well, so then I want to say, let's look at a tangent space to the manifold, and you look at, so F of a fairly small disk could look like this. This is F of a disk, and here's the tangent space. And here's maybe the inverse image of, so this is a disk in V, and here's the inverse image of W maybe cutting through here. And here's the, this was supposed to be the image of this disk, but it's got the wrong, I mean, here's the manifold V, the tangent space of the manifold V. So I want to say that here are the intersections you're interested in, but I want to slide them down until they hit the flat tangent space. So my problem is that as I keep taking images of V, they're getting more and more complicated, so I don't know what they look like. But if I look at the flat tangent spaces and use the derivative, I understand that perfectly well. So I want to look at these points of intersections and slide them down until they intersect with the tangent space. And that's good. I mean, the intersections are transversal, and I can move along them, along the inverse images. So this is somehow f to the minus j of w. I can move. But what might happen is this w might actually look like that. And when I move, I leave the neighborhood. So I want to say that the indices of the intersection with the flat plane are same as the indices with the intersection of the unflat plane, and I can do that if they move down. If they don't reach the bottom, well, then there's two canceling out, but they might reach the bottom but outside of the disk. So now I want to count how many can move outside of the disk. And this formula is going to tell me that when they move outside of the disk, this is a very small height. And so the volume of this disk over here is very small, so the number of points that move out is small on the average. And since I'm only talking about homology classes, I can use one of my H's, move around my manifold as I like, and then make this escape number very small compared to the prediction given by homology. So then I just have to keep counting the linear intersections with the linear, and at the end those will add up, be 1 or minus 1. That's the plan. That's what I'm going to use it to, and I want to use the fact that this little gate here that stops you from getting out is short. And that's just given to you by derivative computations. So small volume, small number of points. Oh, maybe I go back to the theorem. Small volume means the number of points is small. So that's the points that escape. So you might think you're doing like complex analysis. You're going to take a disk, and you're looking at the number of zeros inside the disk, but you move the boundary in. Well, how many points is the boundary crossing? So I want to say if the points are close, the one only looking very close to the boundary, they're all lying in a small area, and there's not going to be many points crossing, so you're not losing too much. Okay?
Thank you. So if anybody wants to make a comment or a question, you need this. You need this. Silence in the room. You knocked us out. How do you say knock down? No? No. So we can, yes.
I can ask a question. No, it's okay. With this? Oh, okay. So what is the relation, if any, between the first problem you described and the second one with the two varieties intersecting at finite points? Is there any direct relation between these two problems?
There should be, but I don't know it. Because in fact it's the intersection of the graph with the diagonal that you're counting. So that might be somehow related to the formula of Bezout's theorem. But I didn't prove Bezout's theorem that way myself. I proved it more by this continuation method consideration, where I took one system that I knew, like, well, you just pick your favorite family like fi of z equals a zi to the di minus z0 to the di. So then you've got di roots of these, and if you take the product, you've got the Bezout number of roots. So now you just take this system F and you connect it to a system G, and as long as you don't cross the discriminant variety, you don't change the number of roots along this homotopy analytic continuum one set to the other. So it says anyone you can connect without crossing the discriminant variety has the same number of roots as this one, but now in the complexes, discriminant variety has complex codimension 1, so real codimension 2. So for almost all 2 points you can connect them by a path that does not cross the discriminant variety, so that proves Bezout's theorem. Another proof of Bezout's theorem would be to count the number of points of intersections like in the Lefschetz formula. And then you might do that with differential forms or something like that. But now the index of every complex root is positive. So that will prove Bezout's theorem for you also. But I didn't prove it that way, and I haven't studied that proof. But I think there must be a connection via the graph and the diagonal argument.
So we can thank Mike again.
Thank you. Thank you all for coming.
Thank you for coming.